गुड इवनिंग स्टूडेंट्स। आज हम लोग मैकेनिक्स ऑफ मटेरियल्स में सिंपली सपोर्टेड बीम पर पॉइंट लोड, यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड और यूनिफॉर्मली वैरिंग लोड की वजह से शेयर फोर्स और बेंडिंग मोमेंट डायग्राम की स्टडी करेंगे कि किस तरह से उसे बनाया जाता है। लास्ट लेक्चर में हम लोगों ने डिस्कस किया था कि कैंटिलीवर बीम पर अगर पॉइंट लोड और यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड या फिर यूनिफॉर्मली वैरिंग लोड अप्लाई हो रहा हो तो हम किस तरह से इसमें शेयर फोर्स और बेंडिंग मोमेंट डायग्राम को बनाते हैं। क्लियर? ओके। तो आज के लेक्चर में हम लोग डिस्कस करेंगे शेयर फोर्स एंड बेंडिंग मोमेंट डायग्राम फॉर simply supported beam. Simply supported beam. इसमें हमारे 3 केसेस हो जाएंगे। फर्स्ट केस, जब शेयर फोर्स डायग्राम बनाए हम सिंपली सपोर्टेड बीम का, जब उसके सेंटर पर पॉइंट लोड लग रहा हो। ओके। फिर हम डिस्कशन करेंगे एक सिंपली सपोर्टेड बीम हैविंग ए यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड एट इट्स होल लेंथ। ओके। तो फर्स्ट केस हम लोग लेते हैं a simply supported beam having a point load at its mid of span, और इस केस में शेयर फोर्स और बेंडिंग मोमेंट डायग्राम कैसे बनता है उसे स्टडी करते हैं। ओके। पॉइंट लोड mid of span. Let us consider a simply supported beam AB of length L. Having a point load at its mid of span of W. Okay. In the case of a simply supported beam, for determining the shear force and bending moment diagram, or for determining the variation of shear force and bending moment uh, in a beam, in a simply supported beam, first of all we have to calculate the reactions at the supports of the beam. For analysis the forces and bending moment, first of all we have to draw the free body diagram of the beam. Okay. अगर हमें इस बीम का फोर्स एनालिसिस करना है तो उसके लिए सबसे पहले कंपलसरी है कि हमें इसके रिएक्शंस, इसके एंड पॉइंट्स पर रिएक्शंस को डिटरमाइन करना होगा। ओके, दैट इज क्लियर। ओके, लेट reactions at points A and B are RA and RB respectively. Okay, now from equilibrium condition we know that if the body is in mechanical equilibrium, then algebraic sum of all the forces about the x-axis is equal to 0. Algebraic sum of all the forces about y-axis should be equal to 0. And moment of all the forces about any point, algebraic sum of moment of all the forces about at any point should be equal to 0. Here there is no force acting in the x direction. So taking the second equation, here at the point A reaction is Ra. Assume at the point C where the point load W is acting, assume that is the point C, okay, and at the point B the reaction is Rb. Now from the equilibrium equation, algebraic sum of all the forces about y-axis is equal to 0. This is our first step for drawing the shear force and bending moment diagram for a simply supported beam. Okay, this is our first step. We have to first calculate the reactions at the end supports. Okay, now on the beam, two forces are acting in upward direction, Ra and Rb. Taking these forces at the left hand side of the equation, and a one force, a point load is acting at the point C in downward direction, and the magnitude of this load is W. This is the equation number 1. Now taking the moment of all the forces about the point uh, B, let's say A. Now taking the moment of all the forces about the point A, the line of action of the force, reaction force Ra, is passing from this point A. So the moment of this force, reaction force about the point A, the bending moment about the point A of this reaction should be equal to 0, because the line of action of the force passing from the point and the perpendicular distance of the line of action of the force and the point is 0. Okay, plus the second force Rb, the second reaction force Rb is acting at the point B, which is at a distance L from the point A. So the moment about the point A of reaction Rb is Rb into L, force into perpendicular distance, equal to this reaction develops a anti-clockwise anti-clockwise movement about the point A. Okay. Now the load W, which is acting at the middle point of the beam at a distance L by 2 from the point A, develops a clockwise movement about the point A. So the moment due to this force is W into L by 2. Moment about the point A of this by this force point load is W into L by 2. Now from this equation, the reaction at the point B will be equal to the W by 2. Putting this value in equation number 1, we will get the magnitude of the reaction force at the point A, Ra, will be equal to the W by 2. Okay. So in the case of a simply supported beam, when a symmetric load is applied, then the reactions at the end points will be half of the total load applied on the simply supported beam. Okay. Now come to the second step. Now the reaction at the point A is W by 2. Reaction at the point B is W by 2. Clear? And a point load W is acting at the middle of the beam. This is the point A, this is the point B, this is the point C. Okay. Now, if we for drawing the shear force and bending moment diagram, we have to consider a section between point A and C first. firstly, and about that section we will derive the equations of shear force and bending moment diagram respect to the distance from the point A. Okay, and after that, applying the end conditions and according to the equation of shear force and bending moment diagram, we will draw the shear force and bending moment diagram, or we will plot the graph between shear force and the length of the beam. Okay, for the section AC. Now after that, we will consider the section between point CB for drawing the shear force and bending moment diagram of the remaining section. Okay, the variation of shear force and bending moment diagram will change between point A to C and C to B, because a point load is acting at the point C. So the effect of this point load in the left hand side of the section is different, and at the right hand side of the section is different. Okay, now consider a section XX at a distance x from the point A. Okay, एक now shear force about the section XX will be equal to the algebraic sum of all the vertical forces about this section, and the sign convention of the forces will be, upward forces will be taken as positive and downward forces will be taken as negative. Okay, here in the left hand side of the section XX there is only a force W by 2 which is acting at the upward direction of the beam. Okay, so the shear force about this section will be is equal to the W by 2 plus W by 2. This is our equation number 1. Okay, now the bending moment about the section XX due to the load W by 2 will be force into perpendicular distance, and distance from the point A of the section is x, and the movement generated by this point load about the section will be in clockwise direction. So the clockwise movement will be positive. Okay, according to the sign convention of the bending moment. Now this is the equation number 2. Okay, for applying the shear force and bending moment diagram, on y-axis shear force and x-axis represent the length of the beam, position of the sections. Okay, and in bending moment diagram, on x-axis there is variation of bending moment, and on x-axis variation of the length of the beam or position of the sections. Okay, now drawing the calculating determining the values of shear force and bending moment diagram at its end point for the section AC. At the point A, x is equal to 0. Now the shear force about the point A will be equal to the plus W by 2, because the shear force is independent from the distance of the section from the point A. And the bending moment about the section A will be equal to 0, because it is depending upon the distance of the section from the point A. Okay. Now the shear force at the point A is plus W by 2, and bending moment about the point A will be is equal to the 0. Now at point C, x is equal to the L by 2. Now the shear force remain constant. Shear force will be is equal to the W by 2, and the bending moment will be equal to the about the point C will be equal to the WL by 4. Okay, WL by 4. Now shear force throughout the section AC remain constant, and the magnitude of shear force is W by 2, and the bending moment at the mid of the span is WL by 4, and at the end point A is 0. This is the bending moment equation is a linear equation, because here the power of the x is equal to 1. So these 2 points will be joined by a straight line. Okay. Now come to the section C to B. We have to calculate the variation of shear force and bending moment about the section between the point CB. Okay. Now for this, again consider a section XX. Consider a section XX at a distance x. X is a variable, okay, from the point A, between point CB. Okay. Now this is an imaginary section about which firstly we have calculating the shear force and bending moment with the variable distance from the point A, which is x. Okay. Now now if we calculating the shear force about the section XX, now there in the left side of this section XX there are two forces. Firstly is W by 2, which is acting in upward direction, and second force is W, which is acting at the point C in downward direction. So the upward force will be taken as a positive force, and downward force will be taken negative force. So the total algebraic sum of the vertical forces about the section XX will be equal to the W by 2 plus minus W. Okay. Now the shear force about the section XX which is the algebraic sum of all the forces, vertical forces, is equal to the minus W by 2. Okay, this is the equation number 3. Now, calculating the bending moment about the section XX, the bending moment about the section XX will be equal to the bending moment due to this reaction force W by 2 will be equal to W by 2 into X, and this force will develop clockwise movement about the section XX. Okay, so this movement will be taken considered as a positive bending moment, and the bending moment due to the point load W will be equal to the now force into perpendicular distance. Now the what is the perpendicular distance between the point loads W and the section? Here the distance from the point A and the here the distance of the section XX from the point A is X, and the distance of the point C from the point A is L by 2. Now the remaining distance will be equal to the X minus L by 2. Now so the perpendicular distance between the load W and the section is X minus L by 2. So the bending moment about the section XX of force W will be W into X minus L by 2. This force develops a counterclockwise bending moment about the section XX, so it will be taken as a negative bending moment according to the sign convention. Okay, for the bending moment analysis. Okay, now the bending moment about the section XX will be equal to the Wx by 2 minus Wx plus Wl by 2. Okay, now Wl by 2 minus Wx by 2. So the bending moment about the section XX will be W by 2 L minus X. This will be the bending moment equation about the section XX for the section CB. This is the equation number 4. Now, applying the end conditions in determining the value of shear force and bending moment at the point C, here x is equal to L by 2. Now, from the equation number 3, we will see that the shear force will be constant throughout the section CB, because it is independent from the variable x. Okay, so the shear force about the point C will be minus W by 2, and the bending moment about this section at the point C will be W by 2 L minus L by 2. Okay, this will be equal to the WL by 4. Clear? The value of bending moment will never uh, the value of bending moment will be constant, uniform. Okay, here at the point C, shear force is minus W by 2 and the bending moment is WL by 4. Now calculating the shear force and bending moment, value of shear force and bending moment about the point B. At point B, x is equal to L. Here shear force is independent from the x. It will be equal to the minus W by 2. Okay, and the bending moment about the point B will be equal to the 0, because W by 2 L minus L. L minus L is 0, so the bending moment about the point B will be equal to the 0. If we see the bending moment equation here, the bending moment equation is a linear equation with respect to the distance x, and because the power of this maximum power of the variable x is 1 here, so the bending moment equation will be a linear equation. So at the point fixed and point B, bending moment is 0. So the point C and at the point B, bending moment will be join with the linear equation, a line, because bending moment equation is a linear equation here, and the shear force will remain uniform, constant throughout the section CB, and the magnitude of the shear force will be minus W by 2. Here, this is the shear force diagram for the simply supported beam having a point load at its mid of its span. Okay, and this will be the the bending moment diagram for the simply supported beam having a point load at its mid of its span. Here, maximum bending moment will occur at the mid of its span. In the case of a cantilever beam, the maximum bending moment will occur at the fixed end. Okay, so at x is equal to L by 2, bending moment will be maximum, and the magnitude of the maximum bending moment in the case of a simply supported beam having a point load at its mid of its span is equal to the WL by 4. Okay, now come to the next problem. Shear force and bending moment diagram of a simply supported beam having a uniformly distributed load at its whole length. Okay, case 2, uniformly distributed load at its whole length. Now, let us consider a simply supported beam AB of length L having a uniformly distributed load at its whole length, and the intensity of this uniformly distributed load is small w Newton per meter. Okay, now first of all, the first step for determining the shear force and bending moment variation between the point AB for the simply supported beam having a uniformly distributed load. First of all, we have to calculate the reactions at the end points. Okay, now let reactions at point A and B are RA and RB respectively. Okay, now applying the equilibrium equation, and for applying the equilibrium equation, before applying the equilibrium equation, we have to convert this uniformly distributed load in point load for analyzing the forces in the beam. Okay, so before analysis the forces, converted this uniformly distributed load in point load. Now here the intensity of uniformly distributed load is W Newton per meter. On 1 meter there is a W Newton load. So if on 1 meter there is W Newton load, then for L meters the total load is W into L. Okay, as we know that the total weight of a body will passing from its center of gravity point and this uniformly distributed load is a symmetric load. So the center of gravity point of this uniformly distributed load will be at its middle of the whole length on which this uniformly distributed load is acting, and in this beam this uniformly distributed load is acting at its whole length. So the total load which is acting due to this uniformly distributed load, which is equal to the W into L, is passing from its mid of span. It means from the point A, L by 2. Okay. Now we can calculate applying the equilibrium equation for this simply supported beam. Okay. Now applying the equilibrium equation, algebraic sum of all the forces about the uh, algebraic sum of all the forces will be equal to 0 for mechanical equilibrium. Here two forces are acting in upward direction. The magnitude of these forces is Ra and Rb, reactions at the end points, and the one force is acting in downward direction, which is W into L due to the uniformly distributed load. Now this is the equation number 1. Now taking moment about the point A of all the forces. So as we already seen in above derivation that the movement about the point A of this reaction force Ra, which is passing from the line of action of this reaction force passing from the point A, will be equal to 0, because the perpendicular distance between the line of action of the force and the point A about which the movement has to be calculated is 0. Okay. Now the moment about the point A due to the reaction Rb will be is equal to Rb into L, because this reaction is at a distance of L from the point A. Now the bending moment movement due to the point load W L acting at a distance L by 2 from the point A. So the reaction at the point B will be is equal to the WL by 2. As we told you already in the above derivation that if the symmetric loading is applying on a simply supported beam, then in that case the reactions at the points will be half of the total load applying on the simply supported beam. So the from the equation number 1, the reactions at the point A will be WL by 2. Now consider a section here. Only one load is applying from the point A to B, which is a uniformly distributed load. So the variation of shear force and bending moment between the point A B will be shown by only one equation of shear force and one equation of bending moment. So considering a section XX at a distance x from the point A. Okay. Second step is, let us consider a section XX at a distance x from the point A. Between AB. Okay. Now for force analysis, first of all we have to convert this uniformly distributed load in point load, as we did in determining the reactions at the endpoints. Okay. Here the uniformly distributed load is acting at x distance. So the total load due to this uniformly distributed load acting at x distance will be W into x. And this load will passing from the center of gravity point of this section x, which is at the middle of the section. It means x by 2. Okay. Now calculating the determining the shear force about the section XX. Here two forces are acting in the left hand side of the section XX. One is WL by 2, which is acting in upward direction. So the upward force will be taken as positive, and the second force is acting in downward direction, and so this force will be taken as negative force, minus Wx. Okay. So the shear force about the section XX will be W L by 2 minus x. Shear force about the section due to this uniformly distributed load is W L by 2 minus x. This is the equation number 3. Now bending moment about the section XX will be equal to the bending moment due to the reaction force WL by 2 about the section will be WL by 2 into x, and this force develops a clockwise bending moment about the section, so it will be taken as a positive, and the bending moment due to the uh, load W into x about the section XX will be Wx into x by 2, because the perpendicular distance between the load and the section is x by 2. Okay. And this force develops a counterclockwise bending moment about the section XX, so it will be taken as a negative bending moment. Okay. So the total bending moment will be equal to the Wx by 2 L minus x. This will be the bending moment about the section XX. This is the equation number 4. Now determine calculating the shear force and bending moment at the end points. Bending moment and x, shear force and x. Now at point A, x is equal to 0. Shear force at the point A will be W L by 2 minus 0. So the shear force about the point A will be WL by 2. Okay. Okay. Now bending moment about the point A will be bending moment about the point A will be 0. because the equation is wx by 2 L minus x. Okay, so the bending shear force is WL by 2 and bending moment is 0. Now calculating the shear force and bending moment at the point B. At point B, x is equal to L. Shear force at the point B will be WL by 2 bracket x minus L by 2 L minus L by 2 minus x. Okay, L by 2 minus x. So L by 2 minus L. So the shear force about the point B will be minus WL by 2. Okay, minus WL by 2. Now the bending moment about the point B will be W x by 2 L minus x. So here W L by 2 L minus L. Now the bending moment about the point B will again equal to the 0. So the at the point A bending moment is 0 and at the point B a bending moment is equal to 0. Both the equations are linear equations. If we seeing the equation number 3 and 4, here x power is maximum, no, here bending moment equation is a parabolic equation and the shear force equation is a linear equation. Okay, so at the point A, at the point A shear force is WL by 2. At the point B shear force is minus WL by 2. These 2 points should be joined with a line because shear force equation is a linear equation. Okay, this will be our shear force diagram for a simply supported beam having a point load at uniformly distributed load at its whole length. Now come to the bending moment variation, bending moment diagram. Here at the point A bending moment is 0 and the point B bending moment is equal to 0, and the variation of bending moment, here the variation of bending moment is a parabolic variation. Okay, but we don't have any other points where the bending moment variation can be determined. Now from the bending moment equation, which is Wx by 2 L minus x, this equation, from this equation we can calculate the point where the bending moment will be maximum. Okay, for determining this, that we will differentiate this equation with respect to x. Okay, we will differentiate this equation with respect to x. So we will get WL by 2 minus W 2W into x by 2. If we putting this value equal to 0, we will get the point where the bending moment is maximum. So WL by 2 minus Wx will be equal to 0. So from here x is equal to L by 2. At x is equal to L by 2, bending moment will be maximum. Okay, bending moment will be maximum at the point x is equal to L by 2. Now calculating the bending moment at x is equal to L by 2 will be is equal to W into L by 2 into 2 L minus L by 2. So it will be equal to WL square by 8. So in the case of a simply supported beam having a uniformly distributed load at its whole length, bending moment will be maximum at the middle of the span, and the magnitude of the bending moment, maximum bending moment, is WL square by 8. Okay. If we see the shear force variation at x is equal to L by 2, shear force is 0. So at this point bending moment is maximum, and the equation of the bending moment is a parabolic equation. So maximum bending moment occurs at the middle of the span of the beam, which is WL square by 8. Okay. So again, in the case of a simply supported beam having having a uniformly distributed load, the bending moment will be maximum at the mid of the span, and the magnitude of the maximum bending moment is WL square by 8. Okay. Now in the case of a cantilever beam, and for a simply supported beam, simply supported beam, bending moment varies a maximum for a point load x, or value of maximum bending moment. So in the case of a cantilever beam at x is equal to L, or say fixed end, maximum bending moment occurs, and the magnitude of bending moment is WL. In the case of a simply supported beam at x is equal to L by 2, or say mid of span, bending moment is maximum, and the magnitude of bending moment is WL by 4 in the case of a point load. In the case of a uniformly distributed load, again at fixed end x is equal to L, in the case of a cantilever beam, bending moment will be maximum, and the magnitude of the bending moment, maximum bending moment, is WL square by 2. Again, in the case of a simply supported beam, bending moment will be maximum at the mid of the span, and the magnitude of the maximum bending moment is WL square by 8. Okay. So these values are very important. Okay, for studying the deflection of the beam, stresses in the beams, and column, when we studying the columns, so these values are very important. Okay, now for the cantilever beam, a uniformly varying load is acting. When the uniformly varying load is acting, uh, we calculate the maximum bending moment at which is at the fixed end, and the magnitude of this bending moment will be uh, W L by 2 into L by 3, WL by L square by 6, WL square by 6. Now, the last derivation for a simply supported beam having a uniformly varying load is remaining. In the next lecture, we will calculate the shear force and bending moment variation for a simply supported beam having a uniformly varying load at its whole length. Okay. So in this chapter, okay, thank you class for